All right, so in this video here, we will be discussing probability distribution. Starting chapter 5. In the previous chapter, when we first introduced probability theory, what is probability? How do we calculate the chance of certain event occur for a given procedure? And we discussed several basic rules. In this chapter, we're going to tie that to statistics a little bit, statistics where we look at procedure and then we're going to discuss the distribution of all the probability for that procedure, and we're going to define what define formally what is a probability distribution. How do we have a procedure that qualify or meet the requirements, and then in six we're going to further discuss this and study more how probability relate to statistics when it comes to normal distribution. But anyway, so let's get back to 5.1. I like to start out this lesson with several definitions and also notation as well when we get to the second part of this. So let's start with the first definition here. We define a variable to be random if it has a single numerical value and it's determined by chance. Okay, for each outcome of a procedure. So given procedure, we can have an outcome that is determined by chance, and the outcome is a number, and U is typically represented by the variable x. So we call that random variable. The second definition would be a random variable considered to be discrete if the possible values of the random variable are counting values or separated like whole numbers. Okay, and we discussed discrete data values early on in the course. In this case, we further tied that concept to a random variable. And then we have a definition of a random variable to be continuous if the values, if the possible values can be taking any values in a certain interval using measurement. So again, we also discussed continuous data value in the previous chapter. In this chapter, we're going to tie those two concepts to a random variable. Let's look at example 1. How do we classify, how do we determine if a given value or variable is indeed a random variable, and whether the random variable is discrete or continuous. So it said identify the following which is the most appropriate discrete random variable, continuous random variable, or not a random variable. So if we look at data values, if we look at procedure of determining exact weights for the next 100 babies born in the United States. So again, we don't know what the exact weight will be for the next 100 babies being born in the United States. So the values of those weights are determined by chance. The values can take up any number in an interval. So it's going to be continuous in that sense. And then it's random in the sense of the value of the weights are randomly determined by chance. We don't know exactly what the weight's going to be. So in A here, we're going to say that we have a continuous random variable. Okay. And part B, responses to survey question, which political party do you prefer? So in this procedure, in this survey here, the results of the survey are the political party that people or people who surveyed response, such as Democratic, Republican, other. So those are named and labeled. In this case, we don't have a random variable because it has to be value, numerical value. Okay, so we say that not a random variable because the results are not numerical. Okay, Next, part C, the number of spins of roulette wheels required to get number 7. That could take 5 spins, 20 spin, depends how lucky you are, but the number of spin that it takes to get number 7 is all determined by chance and are whole numbers. They're not decimal or can't take any value besides just counting numbers. So in this case, we have a discrete random variable. Okay, height of students in statistics classes. In this case, we're gonna have continuous random variable because the height values are randomly determined by chance, and also can take up any values in an interval. So and we have to measure to get the height. So in this case, we have continuous random variable. Okay, eye colors of statistics students. In this case, the result will be different color of eyes, so therefore they're not numerical values. So in this case, we don't have a random variable because in order for their values, in order for a random variable value can be considered to be a random variable, it has to be numerical value. In this case, the eye color of statistics student, this is categorical data. Okay, so hopefully through that example, you can get an idea what is a random variable when we look at a procedure that involve values are determined by chance. Next up, we have notation. In this chapter, x denotes the random variable. Okay, and P of x denotes the probability that a random variable result in a particular value x, and the distribution, a probability distribution is when we look at all the outcomes for a procedure and then display that as a table or graph or formula, which includes all the probability for each possible value of a random variable. So chapter 5, we're going to look at probability distribution for a discrete random variable. And then chapter 6, we look at probability distribution for continuous random variables. It's a little more confusing than discrete. Discrete is more straightforward. However, there's still a lot of formulas involved to calculating probability. But that's what chapter 5 is we're going to study discrete probability distributions. Okay, let's look at example 2 here. Suppose we have two standard 6-sided dice are rolled. Okay, that's the procedure. Let x be the sum of the top faces. Okay, so x be the sum of the dice top faces that come up. For example, if we have 2 and 3, right? So those are the top faces come up from the two sums. So the sum would be 5, right? So x in this case can be 5. So that's what x stands for. Okay, so is x a discrete random variable? Yes, in this case, because the sum of the top faces are randomly determined by chance as you toss the dice, and is considered to be whole numbers or counting values, because you can't have like 5.5 sum, right? It has to be discrete values that come up. So yes, in this case, yes, x is a discrete random variable, okay, because the values are determined by chance and are counting values. Okay, list all possible values for x. So if x refer to the sum of the top faces, we can have as low as 2, because that's where we had 1 and 1 for the dice to land. And then we have 3, which is 2 and 1 and 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 is the max of top faces that we can have for 2 6-sided dice are tossed. Okay, find the probability of x equals 7, meaning find the probability that this getting a sum of 7 when the 2 dice are tossed. So this means find so this refers to the probability of getting a sum 7 when tossing 2 dice. Right? That's what P of x equals 7 stand for. So this requires to know the sample space of this procedure, meaning when we toss 2 dice, how many possible outcomes are there in total for sum of the top faces land. So to find this probability, we have to look at the number of ways sum of 7 can occur for 2 dice out of the the number of total possible outcomes for sum of 2 dice. 2 dice, so 2 dice. Okay, meaning, let's say for a sum of 2, there's only one way. You can get 1 and 1. For a sum of 3, you can get 2 ways, because 2 and 1, and then 1 and 2 for the other dice, assuming that these dice are distinguishable, right? So we can kind of look at this and say, okay, to get sum of 7, we can have 1 and 6, 6 and 1, right? So the same dice can land 1 or 6, so that's 2. Then we do 2 and 5, 5 and 2, 3 and 4, 4 and 3. So it looks like there are 6 different ways you can get sum of 7. And then how many total possible outcomes for a sum of the top faces for tossing 2 dice. I'm gonna let you do this on your own, but I want you to draw a table, okay, and representing the sum of the 2 dices. Okay, 1, 2, 3, 4, 5, 6, and then you just list the sum in the middle here. Let's say you get 2, 3, 4, 5, 6, 7, and then so forth. You fill this table here, and you should get 36 total. Okay, so in this case, the probability of getting a sum of 7 when we toss in 2 dice is 1/6. So that's about 36%. Oh, actually, not 36, but 16%. So roughly 16.67%. Okay. So if we were to construct a table or a formula or a graph that describe this procedure, list all the probability for each of this value of a random variable x here, then that would create a distribution of probability. But we have some requirements coming up here, and that's what we have here. So we can't have, a random probability procedure to be considered distribution. We have to set requirements. Okay. All right. So I'm gonna go ahead and stop on this first video, and I'm gonna start example 3 in the next video.